Hi everyone. So here's another example of a Zener diode in a circuit, and in this example we now have a load resistor in the circuit, okay? And we're going to follow the same process as before, but of course we have to analyze based on the circuit that we have. So our step one is to imagine that the Zener diode is not there and it's just open circuit between these 2 points, okay? And we want to check the voltage at this point here. I'll just call it V test for now. We want to figure out what is the voltage at that point. Would it be enough to turn on the Zener diode? And the difference between what we did in the last example and this one is that there's no longer previously, without the load resistor, no current was flowing when we imagined the Zener gone. But now, even though the Zener is gone, we can still have current flowing in our circuit like this because we have a load resistor, and that provides a path. So we have to take that into account when we're doing this initial analysis. So the voltage at V test here between this point and ground, which are references here, is the supply voltage split between these two resistors, and V test is the voltage across the load resistor. So I can use the voltage divider rule in this case to figure out that that V test is going to equal Vs times RL over RL plus R. Okay, so the voltage is getting split between these two resistors, so that's my total resistance on the bottom of this equation, and it's the voltage across this load resistor that is this voltage, so that's what I'm using the RL on top here. So if we sub in our numbers, we've got 18 volts for Vs, so I'm going to get 18 volts times 100 kilo ohms for RL, 100 kilo ohms, divided by, now remember to bracket this, 100 kilo ohms plus 2.2 kilo ohms. Okay, and if we work that out, we're going to get 17.6 volts. Okay, now 17.6 volts is more than the 12 volts of the Zener diode, so the Zener diode will be on in its reverse biased mode, and therefore the voltage drop across it will be actually the 12 volts of the Zener. So this V out here is going to be 12 volts, right? We're saying therefore, because V test is greater than 12 volts, V out equals 12 volts, and that's our V out when we put this Zener diode back into the circuit. Okay, so the next thing that we should actually find, it doesn't say it here on the screen, but let's go ahead and do it. Let's find our currents in the circuit. So we've got IS here, and this is breaking off into IZ here and IL here. Okay, so let's find those. Now we know that we have 12 volts here because we know the Zener is on and it's a 12 volt Zener, so it's holding the voltage across there to 12 volts. And we know we had 18 volts as the supply voltage here. Okay, so we can find the drop across this resistor. So VR is going to be Vs minus Vz in this case, which is 18 volts minus 12 volts equals 6 volts. And we know that Is is VR divided by R. That's going to be 6 volts divided by 2.2 kilo ohms, and that works out to 2.73 milliamps. Okay, be really careful about your units here. And so we've got IS. Now we can't find IZ next. We have to jump ahead and find RL. And we know that, pick a different color here, we know that the voltage across RL is also the 12 volts because RL is in parallel with the Zener diode. So we know VRL equals VZ equals 12 volts in this case, and I'm not, this isn't something I'm memorizing, right? This is coming out of the arrangement of the circuit itself. So IL is going to equal VRL over RL, which is 12 volts over 100 kilo ohms. That is 0.12 milliamps, or 120 microamps, but let's leave it in milliamps for now because this is also in milliamps. And our last thing to figure out is IZ. So we know that IZ is the source current minus whatever was flowing through the load resistor. So that's going to be our 2.73 milliamps minus 0.12 milliamps equals 2.61 milliamps is what is flowing through the Zener diode. And so we would want to make sure that this is not greater than the maximum current rating of our Zener diode on the spec sheet. Okay? So let's look at one more example here. Okay, so the question here is what is the value of this load resistor? What's the minimum value of RL that will cause the Zener voltage, cause the Zener diode to turn on and start regulating, right? We know this is a 12 volt Zener, and we're assuming again that we have 18 volts supply voltage. So remember, when we assume that the Zener is not there and we're looking between these 2 points and we want to know what this V test is, and we're hoping it's above 12 volts to turn on our Zener diode, this voltage is the voltage across RL in a voltage divider split between R and RL with this supply voltage, right? So what we derived last time was exactly that V test is equal to Vs times RL over R plus RL. Now, in this scenario where we don't know what RL is, we do know Vs, we do know R, and we know V test, because the scenario we're looking at is what's the value of RL that is going to give us, it's going to turn on the Zener diode and cause regulation. Well, we know that that has to be at least 12 volts. So the minimum V test is that will turn on the Zener diode is going to be 12 volts. So that's going to give us our minimum RL if we rearrange this equation and solve for RL. So if I'm going to rearrange this equation and find RL, I'm going to do all the rearranging before I put any numbers in. Okay, that's the easiest way to do it. So I'm going to get V test, and what I'm going to do is I'm going to multiply both sides of this by R plus RL. Because remember, if you do the same thing to both sides of an equation, it remains unchanged, but then on this side those two will cancel out. So I'll end up with V test times R plus RL equals VSRL. I'm going to multiply through the bracket, so V test times R plus V test times RL equals VSRL. Now I want to find RL, which means I've got to combine, wait, that was RL. I've got to combine these two parts of the equation. So I'm going to bring this over to the other side, and when I bring it over, it's going to change sign. So I'm going to end up with VTest times R equals VSRL minus VTest RL, and I'm going to factor out RL. So VTest R equals RL times VS minus VTest. Okay, and now in order to get RL by itself, I'm going to divide both sides by VS minus VTest, which will cancel it out of the one side here, and the final equation that I end up with, and I'll write it up here, I'm going to end up with RL equals VTest over R divided by VS minus VTest. Okay, so at this point I put my values in, and my value of VTest is 12. My value of R is 2.2 kilo ohms. VS is 18 volts minus 12 volts. So what I end up with is that RL is 12 volts over 6 volts times 2. I'm running out of room here. Hang on a second. Oh no, undo. Hang on a sec. Let me just move all that over a bit, and I'll go back to green. So this is going to equal 12 volts over 6 volts times 2.2 kilo ohms, and that simplifies to 2, so it's 2 times 2.2 kilo ohms, which is 4.4 kilo ohms. So the minimum RL that I can have here that will cause 12 volts here, which will allow this Zener to turn on, is 4.4 kilo ohms. Okay, units are important.